Assalamualaikum warahmatullahi ta'ala wabarakatuh. We are from Group 12. We present our mini project dynamic, which is a miniature roller coaster. First of all, I will introduce my group member. The first one is Muhammad Akil Hazir bin Muhammad Hafiz, Muhammad Adam Adha bin Burhanuddin, Arman Majidi bin Muhammad Majidi, and Muhammad Nuzikri Hadif bin Jonan. For the introduction of our project, the miniature roller coaster project specifically apply concept of gravitational potential energy converting into kinetic energy as a marble move along the track. It measure displacement, velocity, acceleration, and time to steady motion change through loops, and curve. The design consider practical factor like minimizing friction, ensuring structural stability, and maintaining smooth transition. By comparing calculate value using kinematic and energy conservation formula with actual experimental data, the project offer a hands-on understanding of Newton's law, especially the second law, which is F equal to ma, and they reinforce the principle of conservation of mechanical energy in dynamic system. Okay, next objective of our project. First is to investigate the kinematic behavior of marble on roller coaster track by analyzing displacement, velocity, acceleration, and energy conversion. Second, to apply principle of Newton's law, energy conservation, and motion equation to predict and compare theoretical versus actual result. And third is understand how design factors like track height, loop curvature, and friction affect motion stability and speed.
Okay, now we will look at the basic theory behind how everything moves in our setup. First up, we have kinematics formula. There is three formula we are dealing when we are dealing with motion. First, we have V equals to U plus AT. This is when we want to find final speed after some time. Second, we have S equal to UT plus 1 over 2 AT square. This is when we want to how far something travel. And the last one, we have V square equals to U square plus 2AS, and we use when we want to find link speed, distance, and acceleration. So we have got two energy formula too. First, potential energy, PE equals to mgh. This is energy something has when it is up high. And the second one, we have kinetic energy, which is Ke equals to 1 over 2 mv square. This is energy of something moving. Now in our system, energy keeps switching between PE and Ke. Like when something rolls down a slope, it loses height but gains speed. Ideally, total energy stay the same, but in the real life we have got friction and air resistance, messing things up a bit. We also use Newton's second law, which is F equals to ma, to figure out the force acting on the object, especially when it's going through loops or climbing inclines. Force diagram help us break all down. Okay, so here what went down when we actually run the test. We drop a parallelogram marble from a height of 0.5 meters. That's equals to point A. From there, it rolled down a slope to point B, shoot through a vertical loop to point C, and then climb a bit to point D. So the track had 4 main checkpoints. First, we have A, which is 50 cm starting point and all potential energy. So next we have B, 0 cm, which is bottom of the slope, and max speed happen here. And third one is C, 30 cm, which is top of the loop and some energy lost because of friction. And the last one, D, 5 cm, end of the track but still moving but slower. So with this experiment, we calculate the velocity and energy each point to see how the marble's energy change. Basically, watching it shift from potential to kinetic and back again, and yeah, some energy got lost along the way, probably due to friction and air drag. But overall, the motion follow what we expect from the theory. Now let's break down the number behind the motion. So first, we use a 0.04 kilogram marble and drop it from 0.5 meters. Using the formula potential energy equal to mgh, we have got potential energy at point A is 0.196 joule. Since all that energy turns into kinetic, at the bottom point B, we use Ke equals to 1 over 2 mv square to find the speed. Speed at point B is 3.13 meter per second. That's the fastest point right at the bottom of the slope. Then at point C, which is 0.2 meter height, we calculate potential energy is 0.078 joule. So the remaining kinetic energy is 0.118 joule. That gives a speed of 2.43 meter per second. So finally at point D, we just have 0.05 meter height, potential energy 0.02 joule, kinetic energy 0.176, and speeds we have 2.197 meter per second. So yeah, the energy keeps shifting between potential and kinetic, and the numbers match that we expected, minus a bit because loss from friction and air resistance.
So I will continue with the discussion for project. The first is we need to know how energy change along the track. So the concept is energy change from potential into kinetic and then into potential energy back. For now, we know that the static head is 50 cm, which is the maximum potential energy, and then at the point A, at the start, maximum potential energy, and then the roller coaster will go slow down to point B at the lowest point. We know that maximum speed, almost all energy is kinetic, and then at the point C, at the loop top, kinetic energy converted back into potential, and then at the point D, at its slope, we know that residual kinetic energy and then reduced speed. So the next one is we'll be comparing ideal and realistic result. There is a two type of energy model. The first one is ideal system, and then the second one is realistic system. So for the ideal system, we assume no energy loss, no friction, and no air resistance. Total mechanical energy is fully conserved, and then we assume speed calculated are maximum possible. So as we can see in the table beside, we know that for the ideal model type, the speed at point B is 330 cm per second. So for the next one is realistic system. In the realistic system, we include friction and roller resistance. Some energy is converted to heat or sound, and then result in lower actual speed. So we can see in our table, realistic model type, we see that at point B, the speed it was 140 cm per second, much lower than the ideal model type. And then we will continue with the result and theoretical consistency. The first one is we will see speed and height relationship follow energy conservation law. The next one is ideal case confirm mechanical energy conservation. Energy will transform from kinetic into potential and then again to kinetic. So, and we will see that the pattern of decreasing speed align with theory. Our simulation offer a clear foundation before real world testing. And then for the last one is demonstrate the value of theoretical model in predicting behavior.
For conclusion, this investigation successfully demonstrated the principle of mechanical energy conservation using a scale roller coaster model. The marble began with 0.196 joule of gravitational motion energy at point A. As it descended the track, this energy was systematically converted into kinetic energy, reaching a maximum theoretical velocity of 3.13 meter per second at point B, the lower section of the track. At higher section, such as the loop apex at point C, the energies existed as a dynamic combination of potential and kinetic, proving the continuous transformation of energy throughout motion. Thus, observation confirmed that the marble motion follow predictable pattern defined by kinematic equation and energy conservation law, thus validating the roller coaster design as both functional and theoretical sound. That all from my group. Thank you.